Hi fam. This is our lesson for standardizing or using the standard normal curve. This is the lesson where I'm hoping that I can bring together for you the relationship between transforming data and using a standard normal table. So I'm going to take a brief trip through the last two lessons and hopefully use that little bit of a review to help you make the connection of why I put these lessons together. So I'm just going to go to my notebook. I have a new divider for you guys once I see you again. This is our standard normal curve. And the first thing that we talked about was transforming data. So we talked about what would happen if we added, subtracted, multiplied, or divided a value from every observation in our data set. And we investigated that through this data. We had the heights of 17 female Army recruits, and we went through and investigated what happens if we subtract a number from every observation, what happens when we divide the observation by a number. And what we discovered is that shape doesn't really change. If we look at all three of these dot plots, when you transform a data set, we haven't seen one that significantly changes the shape of our data. The only thing that we have seen, specifically in this example, was that the shape, or I guess I should say the width of our distribution was more narrow. So it was a shrink, or the spread decreased. So then after we did this, well, pause, sorry, I'm getting a little ahead of myself. In our investigation, one of the biggest takeaways was shape doesn't really change. You can make the distribution wider or more narrow, but the overall shape doesn't change by all that much. And you can move a distribution up or down on the x-axis by adding or subtracting. So that's what we were going through on these pages. We looked at how if you add, you're literally picking up your distribution and moving it to the right by whatever you add by. And it's similar for subtraction, except for you move left. And then we talked about how if you multiply an entire distribution by a number, it spreads your data out. It keeps the same shape, but just spreads that out. And if you divide, you shrink the spread on your distribution, and your distribution becomes closer together. Then we headed into the standard normal curve. And I told you guys that it probably didn't make a whole lot of sense why I went through and talked about how you transform an entire data set, and then all of a sudden we're talking about this thing called the standard normal curve. So the basics of the standard normal curve is that the standard normal curve always has 0, 1, 2, 3 and negative 1, 2, 3 on its x-axis. And this divider that I'm going to give you gives us a good visual of why that is, because this x-axis represents z-scores. Now, z-scores is something that we learned in the previous unit, and a z-score tells you how many standard deviations from the mean an observation is. So this standard normal curve represents all of the z-scores in a distribution. And then our purple table, because there are so many different z-scores that can be calculated, our purple table gives us the percents that match the z-scores. So we just went through and practiced finding those percents. We used a standard normal curve each time. X-axis was always the same. I gave you a z value, you looked up the percent, proportion, or area that matched it. We practiced shading in and labeling And then we practice going backwards. So instead of me giving you a z-score, I give you an area and you have to go and find the z-score. Today is where we connect the two. So to make this connection, let's start at our standardizing note sheet. I'm going to ignore these 3 steps here at the top for now, and I'm just going to look at the prompt. So for example 1, it says the length of human pregnancies from conception to birth varies according to a normal distribution varies according to a distribution that is approximately normal with a mean of 266 and a standard deviation of 16. At what percentile is a pregnancy that lasts 240 days? And then they tell us that's about 8 months. So what we know at this point is the empirical rule. When we have gotten problems like this previously, we would draw our normal curve. So that's what we're going to do. We're going to label it with its parameters. So capital N 266, comma, 16. Then we're going to draw our normal curve. We would put 266 in the middle. And then 1 standard deviation away, we would do 266 plus 16. Puts us at 282. 2 standard deviations away is 298. And 3 standard deviations away is 314. And then we work our way down on the left. So 266 minus 16 gives us 250, 234, and 218. And then what we would do is we would find 240 on our normal curve. So they have given us an x of 240. And what they are asking us to find, so we should say we want to find P of x less than 240. You can put a less than or equals to. I think I'm just going to put a less than. So we would go over to our normal curve and we would plant a flag however you prefer to plant your flag at x is 240. And previous to this, we would have to estimate because they want to know the percentile, which means we have to figure out the area to the left of this flag that we just planted. But what we know in terms of the empirical rule is that this value here is -2 standard deviations away, and this percentile is 2.5%. So a value of 234 is 2.5 percentile because that's how much data is to the left of 234. And 250 is the 16th percentile. So maybe to make our lives easy, I'll round up and say that we know that this gestation length is between the 3rd percentile and the 16th percentile. Previous to what we're going to learn today, that's all we would be able to say about this percentile. We would just be able to estimate, well, it's between 3 and 16. We don't need to estimate anymore, though, because we know that we can transform an entire data set. So coming back to the first investigation we did in this unit, what I was having you do when we went through and subtracted and divided was I was actually having you change every observation in our data set to its z-score. I can take an entire data set, transform it to its z-scores, and it still maintains its shape, and we can get information about our data set that we wouldn't otherwise. So I want to make sure that we're clear on this. What we calculated was that a height of 62 is negative 1.8 standard deviations below the mean. And a height of 63 was negative 1.2, so I guess I should say 1.2 standard deviations below the mean. A height of 65 had a z-score of 0 because it's the same value as the mean, and so on. So in this investigation of transforming data, what I now know is that I can find the z-score for any observation, and I can even find the z-score for just one observation in a data set, which is what we did when we first learned z-score. If you know a distribution's mean and standard deviation, no matter what the size of the data set is, and by size I meant shape, if you know the mean and standard deviation of any distribution, you can always find the z-score for observations. So all we have to do now is connect that to our standard normal curve, which is a graph of z-scores. So we're going to take this observation of 240 and we are going to change it to its z-score. So we're going to say z equals the observation that they give us, 240, subtract the mean of 266, and we're going to divide that by the standard deviation of 16. When we plug that in our calculator, this gives us a z-score of negative 1.625. Okay, so now let's see how this matches up to what we already have. On this normal curve, the mean of 66 has a z-score of 0. The z-score for 282 should be 1. I'm going to plug that in really quick and see if that works. I would do 282 subtract 266 divided by standard deviation, and this actually does give us a z-score of 1. 298 would give us a z-score of 2. 314 would give us a z-score of 3. 250, let's plug that one in. 250 subtract 266 equals negative 16. Divide that by standard deviation, you get negative 1. Negative 2, negative 3. So these values now match up. We have our original data values matched up with z-score values. I wish that we were together right now so that I could verify that you understand, because this is an important idea. For the specific observation that they're asking about, we got a z of -1625. So let's see if our flag was in that area. It is. We did a pretty good job of planting our flag where it should be. So now let's label this with its matching z-score. So an x of 240 has a z-score of -163. Okay, well, if we have a z-score, what we can do now is use our purple table. So we can use, sorry, I'm trying to zoom out, the standard normal table to find the percent below a z of -163. So we're going to use our z table to find this area I just shaded in. So we go to our z table, we go down to -1.6, we go over to 3, and I'm getting 0.0516. And now I know the percentile or the solution to this problem, because this is equal to this. How do I know that? Because those are the same spot on the normal curve. So to answer this question now, I need to write out a sentence. So let's decide what percentile we think this is. If we have 0.0516, I'm going to say that this is about 5%. So now I'm going to write a sentence answering this question. A pregnancy that lasts 240 days is at the 5th percentile. We could even change this to say at about the 5th percentile. So how we bring our two lessons together is seen right here. I can transform this observation into a z-score and use the standard normal table to estimate the percent or the percentile for that value. Now we can go up to the top and revisit what I had you skip. What we just did was called standardizing. We took 240 and we standardized it. And we got a standardized score of -1.625. We refer to it as a z-score, but really a z-score is a standardized score. So when we standardize, we need to shade a normal curve and label all of the things. And what I would like you to notice is that all of the things is bolded. Why is that bolded? Because everything that we labeled down here needs to be labeled on every single curve. You need to have the parameters, the flag labeled with both your X and Z, the axis labeled with both your X and Z. Next, you find Z-score, and you got to show all the work. Every little step that you had to take to find Z needs to be very clearly labeled. One thing that I see that can get you guys into trouble is that when you're finding Z, you actually need to label that Z equals. You cannot just say 240 minus 266 divided by 16. You have to put Z equals on the front of that. So here we showed all of our work. And then lastly, you want to answer the question with a well-written sentence that includes context. So you cannot just say 5th percentile and move on with your life. You have to write a nice sentence. And you typically will use the same wording that the prompt gives you. So at what percentile is a pregnancy that lasts 240 days? I just use that exact phrasing. A pregnancy that lasts 240 days is at about the 5th percentile. The last thing that I want to do before I move on with this problem is just verify that where we started was correct. We started this problem by using the empirical rule and saying, I said, I know that our percentile is between the 3rd and the 16th percentile. We did end up getting a percentile that fell within that interval. All right, so now all of our other problems are standardizing. There is nothing really new or crazy. We are going to combine this process of using area and this process of planting our flags and shading in to answer more real-world questions. So our next question is, what percent of pregnancies last between 240 and 270 days? So even though we have our curve already drawn and labeled above, unfortunately, we got to do it again because what we're shading in is different. So I list my parameters. I draw my curve. On this one, I'm going to list my Z values first because that's just that's my preference, and because that's what we use to find the probability or percent. So I'm going to start with 0, 1, 2, 3, and then underneath that, I will put the actual values of 266, 2. Okay, I'm done labeling. They gave us a lower bound. So I'm going to say X lower bound is equal to 240, comma, X upper bound is equal to 270. And they want us to find the percent of data between the lower bound and the upper bound. So when we were at this step last time, we would change these to their Z-scores now. So I'm going to say Z of our lower bound is equal to negative 1.63. Why didn't I write down any work? So next to that, I'm writing C calculation above. because this is the value that they gave us in the last problem. Z of our upper bound, make sure you're labeling those, lower bound and upper bound, is 270 minus 266 divided by 16. That gives us a Z of 0.25. So now I'm going to plant those in or on my normal curve. So my first one is at negative 163. And I label it with both values. This is an X of 240 or a Z of negative 163. And my other one is at 0.25. This is an X of 270 and a Z of 0.25. And they are asking us to find the area between, which we do need to shade in. Okay, well, in order to calculate this, we need to find P of the lower bound and the percent of the upper bound. So the percent of Z lower bound less than, I guess I don't need to write LB there. I can just say percent of Z less than negative 163 was 0.516 from the last problem, comma, percent of Z less than 0.25. We go to our table, go down to 0.2, over to 0.5, and that is 5987. So now we can put this together. The percent of data that is between a Z of negative 163 and 0.25 is 5987 subtract 0.516. That gives us a percent of 5471. I'm going to highlight these, indicating that I know that these are the same. So now we end with our well-written sentence. So what percent, well, we just found 5471. So we're going to say about 54.71%. And then I'm going right from the prompt of pregnancies last between 240 and 270 days. Okay, so both of these problems hopefully are a good representation of why we did our last, or not why we did our last two, but why I included transforming data in this unit. Because if we were not able to transform data, we wouldn't be able to use our z-table in this way. So we transform our data into z-scores and then use a z-table to find the probabilities we want. Okay, next up, how long do the longest 20% of pregnancies last? Oh boy. Okay, how long are our longest 20% of pregnancies? All right, well, what the longest 20% of pregnancies would be is 20% to the right of x. So they want us to find x, and the longest 20% would be 20% of the data to the right of x. Well, in our standard normal table, it doesn't give us areas to the right. It always gives us areas to the left. So what we're going to use is then 80% is to the left of x. We're still in our same data set, so we still have same normal curve. Redraw it though, because this time they're asking about different things. We list our parameter, 266 and 16. We label the bottom. I always do z's first. Then underneath that, I list the actual data. Okay. 80% is equal to 0.80, which you guys know I changed so that it looks like thousands. So I'm going to the table to find the z that corresponds to an area of 0.8000. Hopefully you're looking too. Okay, I got a z of 0.84. So I guess I can say then z of that area is 0.84. Is that right? Double check me. So you guys know how I make a zillion mistakes. I put z of a here because I'm trying to indicate that I know that this z matches this area. Okay, so now let's label this. We have a z at 0.84. And they're asking us to find the x that matches that. This z of 0.84 represents 20% of the data to the right and 80% of the data to the left. My flag is very crooked on this problem, please forgive me. Okay, well, whenever we're working with z-score, we know we have a z, an x bar, and a standard deviation. I think we're supposed to be using mu and sigma actually, fam. I think we're supposed to be going mu, sigma. Okay, well, we know z now. They want us to find x. We know mu. We know sigma. So now we have to use the formula to find x. So we have 0.84 equals x minus 266 divided by 16. Okay, we multiply both sides by 16. And I don't show that on my paper only because I want you guys to know where we started. So I worry that if I write times 16 times 16, then it's harder for you guys to understand what did I write down at first. 0.84 times 16 is 13.44 equals x minus 266. Then we add 266 to both sides, and we get 27944 equals x. And now I can use that to answer the question. So how long do the longest 20% of pregnancies last? So the longest %% of pregnancies last about 279.44 days. And then I'm going to double check that I have labeled this sufficiently to show my understanding of how I use the normal curve to do this. Okay, we have a new data set on our next problem. We're getting away from the pregnancies, and now we're going to do a problem on lids for fast food restaurants. So at some fast food restaurants, customers who want a lid for their drinks get them from a large stack left near straws, napkins, and condiments. The lids are made with a small amount of flexibility so they can be stretched across the mouth of the cup and then snugly secured. When lids are too small or too large, customers can get very frustrated, especially if they end up spilling. At one restaurant, large drink cups require lids with a diameter between 3.9 and 4.05. Sorry, by 3.9 I meant 3.95 and 4.05. So the smallest it can be is 3.95 inches. And the largest it can be is 4.05 inches, which is a very, such a small distance, such a small measurement of length. The restaurant's lid supplier claims that the diameter of their lids follows a normal distribution with mean 3.98 and sigma 0.02. Assume that the supplier is telling the truth. What percent of large lids are too small to fit? So we are looking at the percent of lids that will be too small. Okay, so the required diameter is 395 on the lower end and 4.05 on the upper end. So the lower bound, the required lower bound is 3.95. So that would mean that too small is any x that is less than 3.95. So we want to find the percent of x less than 395. Everything that I'm writing down is required. You want to explain as much as possible. I know that it's cumbersome, but it is required. Okay, now we draw and label all the things. I list my parameters, 398, 0.02. I put my z-scores down first. Then I go through and put my actual distribution values. If you're not at the same spot as me, just pause and come back when you're finished. So we have to find our z that matches 395. So we're doing 395 subtract 398 divided by standard deviation of 0.02. This is going to give us a z-score of negative 1.5. Before I forget, I know it's a little bit late in the game for this, but I think I just assumed that we all felt good with this formula. The formula for z in this case is x minus mu divided by sigma. So that's what I'm using every time. Okay, so now I do the percent of z less than negative 1.5 equals, and I guess I better fill this in. So I need a flag at 395. That matches an x of 395 and a z of negative 1.5, and I am finding the area to the left. From my normal curve, I get 0.0668. So now I can answer the question. About 6.68% of large lids are too small to fit. That's kind of a lot. It's kind of a big percent. I don't know how I feel about that. Okay. Couple more problems and then you have your check for understanding. Maybe we should take a break. Everybody take a break. I'm going to pause and get a drink. You pause and maybe check your Grammy, look at your Snapchat, pet your dog, but take a little break because we're 45 minutes in, so break. Ready, break. Okay, I'm back. Now it's going to ask us, or now it is asking us, what percent of large lids are too big to fit? So last time we were looking at too small. This time we're looking at too big. So our required upper bound was 4.05. Which means that too big is any X, so any lid that is greater than 4.05. So we want to find the percent of lids that are bigger than that. How do we do that? We calculate Z. X, 4.05, subtract mean, 3.98, divided by standard deviation of 0.02. This gives us a z-score of 3.5. That's a very large z-score. So now that I have all of my information, I'm going to fill all that in. And I know that I typically go faster than you guys. I think it's because I've drawn so many normal curves that I just go really fast. Okay, this brings up something that I saw on your exam too that I do think is helpful to talk about. This is an X of 4.05 and a Z of 3.5. And on your last exam, some of you guys were saying things that led me to believe that you think that the normal curve ends there. So I'm going to go back to our normal distribution. And I just want to highlight for you guys that your normal distribution does not end at 3 sigma and negative 3 sigma. There is still data to the left and right of those values. The issue is that the amount of data is so small. Look at how much data is past 3 standard deviations. 0.15. So if you have a large data set, you will have some values out there. And if you have a really small data set, you might not have any. But here's the takeaway from that. There is data, or can be data, that is more than 3 sigmas away. You had a question that says, was this amount of sleep unusual? The amount of sleep was like 12 hours. And if you calculated the z-score that went with that, you had a z of like 4.5. So 4.5 standard deviations away. And lots of you guys were saying things like, well, that's impossible, or there's no data there, or you just drew a picture and didn't explain why is 4.54 for z so unusual. And the reason why is because very little data is that far away from the mean. Also, it's a pretty well accepted standard that anything past 3 standard deviations is an outlier. So you also could have said a point that is that far out is probably an outlier. So I was reminded of that because of this problem, because he is past the sigmas that we label, but that doesn't mean that this normal curve ends at 3 and -3. It can go on forever. We could have a lid that's 10 feet wide. I mean, we wouldn't, but in theory, you could. So the normal curves don't end at 3 sigmas. It's just that beyond 3 sigma, it is very unusual to find data values there. It's so unusual that there's nothing for me to even shade. Like, there's no part of that curve that makes sense for me to shade. So I'm going to go now to my normal curve. And I want you guys to notice that it doesn't even go as high as 3.5. So if you ever get a question on your exam, in class, on any homework problems, and the number is not on your z-table, the area is 0. You should just estimate that it's 0. So in this case, I'm going to use I'm going to use 9998 because that is very, very close. So I'm going to say, because they wanted 3.5 and this is 3.49. So I think that's close enough, and I'm going to say that this area then is 9998. So probability of getting a z value greater than 3.5 is 1 minus 0.9998. which is 0.0002, which is basically 0. It's not 0, but it's basically 0. And we can finish this up with the statement about 0.02% of large lids are too large to fit. Please make sure that you understand that this is not 2%. We're basically saying about none of the lids are too large to fit. This is such a small percent. It's less than 1%. So it seems like we have some issues with our small lids. We got like 7% of our small lids not fitting, but very little of our large lids. Like in a pack of 1,000, you have 2 that won't fit. So now we're going to do a problem that is similar to one that you will see in your Can You Do, and it's a little bit challenging. It is on the same data. So we're still looking at this lid supplier. The supplier is considering 2 changes to reduce the percent of its large cup lids that are too small to 1%. So we have large lids being too big is like less than 1%, but our large lids being too small is too high. We want to take it from like 7% down to 1%. So we want to change this area here from 7% to 1%. One strategy is to adjust the mean of the diameter of its lids. Another option is to alter the production process, thereby decreasing the standard deviation of the lid diameters. So what they're saying is we need to get this down, this area down to 1%. And there's two options for that. Number one, we can adjust the mean size of our diameter, or we can alter the production process so that the standard deviation is less spread out. So we can either change the mean, or we can change the standard deviation or the error from the mean. If standard deviation is supposed to remain the same, so right here they're telling us, keep standard deviation at 0.02. What value should the supplier set the mean to so that the percent is down to 1%? So this is telling us that we need to find mu. They are asking us to find mu. So let's list what we know. Number one, we know that we have a normal distribution of 398 and 0.02. We can draw our normal curve and then list the actual data values. So we know our distribution. We know our lower bound. Our lower bound is our X value, and that is 395. That doesn't change. So the lower bound will stay the same. Our sigma will also stay the same. They are asking us to find mu, which means that we need to figure out what Z is. Well, we know that because if we need to find, or if we need to adjust the area to 1%, what that means is we need to find the Z that has 1% to the left of it. So area is 1%, which is the same as 0.01, which is the same as 0.0100. So we need to find a Z that matches that A. Okay, so we're going in our table, and it's going to be on the negative side way over here. So let's go to our negative side, and we are looking for 100. So like this number is 75. Oh, look, there's 99. So that's 1 away, and there's 102. So that's 2 away. So I'm going to go with negative 2.33. And then I'm going to label it. So this is the boundary for which 1% is to the left. This is also an x of 3.95. So what we then need to do is find the mean that would give us this z-score. So we have z of negative 233 is equal to 395 subtract mu over sigma. So this is the first one where we actually have to find mu. So let me recap really quick. We want to reduce the percent that we found on example 2A to 1% instead of 7%. But the company wants us to do that by changing the mean diameter of the lids that are produced. So what do we know? We know our lower bound. We know the sigma on our distribution. So then that means I can't even draw this. Teacher, this does not even apply, family. Let me show you what part does not apply. This. We don't know this. We don't know this yet. Sorry, family. So really all we can draw on our normal curve was the -3, -2, -1, 1, 2, 3, 0 in the middle. Okay, so we know the lower bound. We know the sigma. We do not know mu. We can calculate z given the percent that they want us to reduce it to. Okay, let's go from there. I apologize. I guess my break didn't do me any good. Negative 2.33 times 0.02 is negative 0.0466. That equals 3.95 minus mu. Okay, well now you need to subtract 3.95 from both sides. We need to subtract 3.95. So this gives us negative 3.9966 equals negative mu. So our mu has to be about 4. So I'll keep it as 39966 here, but that's going to need to be rounded up to 4. So now let's see if that makes sense over here. Would it make sense for this to be 4, 402, 404, 406, 3.8, just kidding, 3.98, 3.96, 3.94, and negative 3.95 is in the right position now. Okay, I feel okay about that. Hopefully you guys feel okay about that. So our mu needs to be about 4. So now we got to answer that with a nice sentence. The supplier should set the mean diameter to 4 inches, or you can say about 4 inches. You can even say 3.9966 inches. To reduce the percent I feel like there was a better way to write this. I think we should have said to reduce the percent of large lids that are too small to fit to 1%. So I guess it works either way. The supplier should set the mean diameter to 4 inches to reduce the percent of its lids that are too small to fit to 1%. I am sure that there is somebody right now sitting there that's like, Miss Vore, good golly, Miss Molly, I can write that way better than you. Please do. Please write it in your own way, because I don't feel like my sentence was really like winning a gold medal for English or anything like that. But essentially, the supplier should set the mean diameter to 4 inches to reduce the percent of lids that don't fit to 1%. That is a mouthful. However you want to word that is good. You can start with to reduce the amount or the percent of lids that are too small to fit to 1%. The supplier should blah, blah, blah. I can't think of any other way. So, okay, so now you're going to try 2 on your own before you go and do the can you do for this. So the first one is, what percent of Tiger's drives last at least or travel at least 290 yards? So this is like, I'm trying to find one that matches it. This is like the lids that are too big to fit. You could follow that one if you wanted to. And then, what's the third quartile of the distribution? Just remember that Q3 is 75%. So you work backward. So really pause on these and try them. Then come back, check answer. Okay, so before we finish this up, just, you guys know this, I made mistakes on Can You Do 9. Some of you guys were very nice to let me know and double check what my answer said and what they should be. If you are getting something different than me and you've double checked, you should trust yourself. And if you're concerned, just email me and I'll check my work. So before we check these answers, just know I make mistakes all the time. You know that. I don't even need to say that. So if something's not matching up, trust yourself, double check with me. Okay. For Tiger Woods, the percent of drives that travel at least 290 yards, I got 95.99%. So I'm basically just going to leave all of my work up for you to just double check against yours. If I've done something wrong, somebody will just let me know. And then for number 2, third quartile is the 75th percentile. So you want to find the z-score that matches an area of 0.7500. I went through and labeled all my things and got a third quartile of about 97.18 centimeters. So if you need help with this or I've made a mistake, get those addressed before you do the Can You Do. The Can You Do, I think, is 6 problems, but as you can tell, we just did 6 problems and you guys have spent over an hour on this. The cumbersome thing about this is that you got to label the normal curve a bunch and then show all your calculations, but I think that it's doable. If something's wrong with the check for understanding, like I said, get that cleared up before you jump into the can you do. Otherwise, I'll see you in the can you do. Please bless, I did not make any mistakes in this lesson, aside from the normal curve that I labeled wrong. Okay, love you guys. Miss